He's primarily a professor of mathematics at the University of Pennsylvania, chairship position. A member of National Academy of Sciences and the recipient of a number of fellowships, Guggenheim Fellowship and Sloan Fellowship a couple of years ago. Foreign member of the Danish Royal Academy of Science and Norwegian Academy of Science and Letters, and also the recipient of a Field Prize by the American Mathematical Society. It's my great pleasure to be with Professor Kadison. We're going to talk about quantum mechanics and relationship to time frequency.
Thanks for the kind words. Maybe you deserve. Yes. Begin with thanks for the kind invitation to be here, and special thanks to the organizers. For me, anyway, it's a pleasure to be here with all of you. I hope it will become a pleasure for all of you as I lecture. I'll try to keep the lecture gentle and understandable. Don't know how to proceed. Paula Yearns reminded me, only a year or so back, that told me, I don't know whether I knew it or not, that Feynman had said anybody who says he, roughly speaking, anybody who says he understands quantum mechanics is to be regarded with suspicion. and I don't know why he said that. I'm serious to say that. And I would add to that, anybody who plans to teach you anything at all about that in an hour lecture is to be regarded with scorn. I will be happy if you cut me a little slack. So, the underlying, well, I better say this first. Can you make that out? I guess we can go past the title, past the name. No, it's just that it's. Oh, I see. This chair is. Oh, this chair. If you want to do that, you're going to have to move them over. Yeah, a little bit.
You can just move there if that angels.
We can end the lecture quickly. It's like the day everyone's tired. Right, that's it. Okay. So the underlying theme of this is the fundamentals of quantum mechanics, more precisely quantum measurement theory, via the approach advocated by Dirac, let me add in Neumann. Most of the lecture you'll be seeing Dirac, and you will actually be seeing pages from Dirac's third edition. That's the one I was chewing on, graduate student. And the underlying mathematical theme could be said to be an attempt to understand what an orthonormal basis is for a Hilbert space in its broadest sense. Now, that was a project that Iz Singer and I were engaged in as graduate students together during that period of time, and continued, I guess, throughout most of our life, on and off over the years. We've been thinking about that. Problems arose. We settled some of them, and in the process, as always happens with good problems, you have more problems coming up. One of those problems has turned out to be vexing. A nice little pleonasm. Very vexing. It's been around for 50 years. A lot of people have worked on it. And when Rado asked me to come give this talk, he suggested that people might like to hear what has become known as the Kadison-Singer problem from me in some sort of detail, some form. So I assure you that those two underlying themes, physics theme and mathematics theme, are exactly related to that problem. That's where they came. They came right out, the problem came basically right out of Dirac's book. And I'll show you about that in just a moment. So, as a matter of fact, let me try to do that right now. Now, you notice the slides that I have here. It's not the lowest tech slide you can imagine. We had a wonderful lecture from Pala this morning that may have been close to. No, I heard a lecture by Kirchberg one time at the Congress. Those slides had to be seen to be believed. What's coming next? Yeah. What's coming next? Pete wants to know what's coming next, and I'll show you. This is right out of Dirac's book, and you may think that slide, some people claim that sort of stuff has been made by an old monk. I deny all rumors from previous lives. Well, but anyway, I thought it might be appropriate to let you see page 7475 in this third edition. He was in a program to put the mathematical model for quantum mechanics, good working mathematical model, good enough for him to get the positron out in the Nobel Prize. And he was improving that model as I observed all through his life. So the first edition was lower form, the second, so on and so forth. And this edition is, as they say, it's the one I was chewing on as a graduate student. I bought the book for about $2 at that time. It has 4 different $2 today's. I looked at it, his thing. We thought about this, tried to understand what Dirac was saying. Well, anyway, this is it. To introduce a representation in practice. What is he talking about when he says representation? He's really talking about choosing an orthonormal basis. And the idea of representation really isn't so strange. Once you've chosen an orthonormal basis, your linear operators, your bounded operators, unbounded operators as well, Hilbert space, can be assigned a matrix according to the usual way we will learn this in linear algebra these days. And I teach my linear algebra to students, still doing it, did it the year before last. I teach them that choosing a basis actually gives you a representation of the algebra of linear transformations as matrices acting on Rn or Cn, sort of matrices you're dealing with. It's actually a homomorphism. So it is a representation. But that's what Dirac has in mind. Now, Dirac is talking very freely and loosely about these things. It's actually miraculous that he's staying so close to what's right, because he was guided by experiments, the early experimenters, and by what I've concluded was a vastly evolved technical understanding of what used to be called analytical dynamics, classical dynamics. We'll see some of that in a short while under some things that he's done. So he says we look for observables which we would like to have diagonal. So orthonormal bases. So the first thing you can say about orthonormal bases, and I certainly should say this in this gathering, there are special orthonormal bases, trigonometric functions, that with the property that when you expand functions in terms of them, you get a nice representation of the functions. I don't have to sell that here at all. We're talking about Fourier series, we're talking about the beginnings of Fourier analysis. So you will have special bases, and it's interesting to expand things in terms of those special bases. That's one use of orthonormal bases. Dirac is here pointing out another use that we've all seen. You sometimes want to select your orthonormal basis to do something for you, such as diagonalize an operator or a family of operators, and that's what the observables are in Dirac's language. I'll say more about that. And you do so because you're interested in their probabilities, well, say a little bit, or for reasons of mathematical simplicity. You can then treat them as functions, multiply them together, and so on and so forth. But if you're going to diagonalize simultaneously, diagonalize a certain number of these observables and get matrices, the observables had better commute, because diagonal matrices commute. And well, while I've got it up there, I guess I can say Dirac is here inventing for himself Zorn's lemma. You're watching him there. Back in the 30s, doing Zorn's lemma. See? He says, in this nice, airy, physical style, he says, we then see that they form a complete commuting set. C meaning is we make sure that they form a complete. See to it that they form a complete commuting set. And if not, we add some more commuting observables to them to make them into a complete commuting set. So here is Zorn and the rest of us adding in C or 2 to the C as we need from time to time to make a maximal object. And Dirac, in good physical style, although he had his PhD in mathematics. Dirac in good, in English PhD. Take that for what you want. Dirac is sort of airily saying some more, like 2 to the C more, C more. See the cardinality. And in this process, he's also inventing something that's dearly beloved of all operator algebraists. He's inventing the maximal abelian self-adjoint algebra of operators, what we call the MASA, M-A-S-A, just for short. Family of operators, it's closed under the adjoint. An algebra of operators is commutative, closed under the adjoint operation. Bounded operators on some Hilbert space, with the property that if anything commutes with them, then it too is in the algebra. Maximal abelian. Also, it's maximal among the abelian algebras that are closed under the adjoint operation. And that, by the way, makes them maximal among the special class. They're not all maximal. That's what Dirac is doing here. And then, down at the bottom, well, next step 4, he says, we set up an orthogonal representation. That means an orthogonal, it means an orthonormal basis that scratch the normal for the moment. We set up, let me say it, because I can't bring it out of my mouth without saying an orthonormal basis that will diagonalize this complete commuting set. Now, I'm going to talk about maximal abelian algebras in a moment, and we'll have a chance to set up some notation for that. But so let me call the algebra of the algebra of diagonal n by n matrices complex. Let me call that algebra script A cap A sub n. If you have a maximal abelian self-adjoint algebra of n by n matrices, you can choose an orthonormal basis so that it will be diagonal. That's a good way to teach linear algebra. Complex case. If you're an algebraist, you talk semi-simple, start doing things the right way. But you can also do an operator algebra style. And then you have your simultaneous spectral theorem. You can do all kinds of nice things, showing the students sorts of things. So it is possible to do that in this case. Also, if your algebra, if your MASA is on an infinite dimensional, but separable Hilbert space, and it's maximal abelian, and it has lots of minimal projections in it. Projections that are not zero, but such that there's no projection in the algebra that's properly smaller. Has lots of them. How many? Well, enough to add up to the identity operator. The notation we'll use for that is script cap A sub D, D for discrete. Has a lot of atoms. Then, if you recognize your algebra as being of this type, generated by its minimal projections, it is then again possible to find a genuine orthonormal basis that will simultaneously diagonalize it. But, and that seems like, well, you know, that's like finite matrices. What the heck? Might as well be dealing with finite matrices. We'll see. People trying to get around some of the things that come up for the last 50 years. They say that's the problem. And I'll show you that problem in just a moment. He then says, and here's where the problem is. Here's where the problem is. He then says the representation is then completely determined for arbitrary phase factors. By the way, how unique is this orthonormal basis that you get in the finite dimensional case? Well, you get n unit vectors mutually orthogonal, pairwise orthogonal. Is there another basis that will also diagonalize it? Yes, but here's all you can do. You can change each vector by a multiple of modulus 1. That's not going to make any difference. And it's certainly not going to make any difference to Dirac. He says, for most purposes, the arbitrary phase factors are unimportant because they're appearing, the vectors are appearing in inner products, in expectation functionals, calculating the expectation of observables. Those are the numbers that the physicists want. And the phase factors just disappear. One comes out as complex conjugate, and the other comes out as it is, and they're modulus 1, and they're just gone. You don't see them there. So to that extent, you can change the basis. And this is what Dirac is saying here. He's saying the basis is unique of the phase factors. And that's where the question comes in. Because Dirac is not talking just about the case of the observables that can be modeled by AN and AD, simultaneously observables that can be modeled in that way. He's also talking about the cases we'll see in a moment where the observables have what he calls ranges in their spectrum. Observable may have what he calls a range. This is an interval of positive length in its spectrum. But there are mysterious things even in the AD case. We'll talk about that. But Dirac is much concerned about that. For example, now I think it's time for me to back up a little bit and talk to you about what he's saying about observables, what he's saying about modeling physics. I've gotten way ahead of myself in some of this slides and slides out. Okay, is this firmly fixed in your mind, this page? Because it's coming back again. It will haunt you for the rest of the hour. Okay. So we've essentially seen this. It's eerie, the lecture Professor Moran just a short while ago. I mean, so many of the things he was talking about come up again. I was sitting there listening to it. His bases, the orthogonal function bases talking about were also about to appear, slide to us. So there's the Fourier basis up there, and the Hermite, the Legendre, yeah, so on and so forth. And I call those discrete bases. But Dirac is also interested in continuous bases. That's why he says orthogonal bases. He wants his functions, he wants his vectors to be orthogonal. But they can't be normalized, unit vectors. In fact, they have to have infinite length for him. And in fact, you will soon see where he is inventing the Dirac delta function. Again, in Monk script. And these are what we is and I refer to as continuous bases. So if you have an operator with spectrum, the unit interval 0, 1, for example, you're not separable Hilbert space, an orthonormal basis of vectors, it's going to give you every one of the real numbers in there. The operator being diagonal. C of those numbers. The orthonormal basis can have it most often know it. So, where are we? So I've shown you Dirac. I've shown you the other side of Dirac. Now, at this point, I guess I can break down Dirac's. I promised you some more monk script. Because I also promised that this slide was coming back again. This is on page 57 and 58. He says, we have not yet, so he's beginning to try and set up his style of continuous orthonormal basis. And we have not yet considered the lengths of the basic vectors. With an orthogonal representation, the natural thing to do is to normalize the basic vectors rather than leave their lengths arbitrary, and so introduce a further stage of simplification. It's marvelous. Hey, his handwriting's very however, it is possible to normalize them only if the parameters which label them all take on discrete values. If any of these parameters are continuous variables that can take on all values in a range, so you see he's using range for an interval of positive length. The basic vectors are eigenvectors of some observable belonging to eigenvalues in a range and are of infinite length. So these are the Dirac delta functions. Here he is. And you know, they're not so bad. You can use them for certain kinds of calculations if you're skillful. You can do quite a few things that are handy and whatnot. But they are just not mathematical enough to do some delicate things that arise. For example, the question of uniqueness that you raised before. There is a mathematical technique for accomplishing, well, I hear somebody, indeed, mumbling distributions, and I guess Laurent Schwartz, who was a friend, got the fields, one of the first fields prizes after the Congress was reconstituted, he and Apley Selberg, back in 1950, that was the Harvard Congress, for the distributions, which made pretty honest stuff out of what Dirac is doing here, the delta function. But I have to tell you that it's not sweet enough. It's not quite. Someone went musical. There is a much better way of doing it, and thanks to my dear old friend, Kala, this morning, I don't have to do that much with them. It's the mathematical theory of states as they appear in the theory of operator algebras. It is beautiful. And there are two absolutely wonderful side issues associated with these states. Number one, there's an enormous technique that has developed. We know some fantastic stuff. That business has not even begun to be plumbed for purposes of analysis. So what we know about states in conjunction with operator algebras. Halle showed you one of them. He showed you, first of all, he showed you the Gelfand-Neumark theorem, and he then showed you the GNS construction. By the way, I didn't know these things were happening. Really fortuitous. Back in Moran's talk, Halle's. But I took exception to one comment that Paula made. In fact, I like to say I resemble that remark. He said, we teach the Gelfand-Neumark theorem in C-star algebra kindergarten. Yeah. Okay, you remember that? All right. Okay. Now, Paula, here is a challenge for you. I defy you and anybody else in the state of Maryland. I guess I won't include Pennsylvania. So, go to the blackboard and in a finite amount of time, use the key axiom and I'm going to be very careful now.
Square.
No. That was not the Gelfand. Gelfand. Well, I'll defy you. I'll give you the square. And I'll defy you to prove it without that. No, I think I felt a little under. I understood what you were doing. But you see, in their article, 1943 Spornic article, Gelfand and Neumark, far afield now, have a footnote saying they assume this and they assume star is isometric. And in fact, it's trivial, basically trivial observation, but this will come out of this. And those two became, for a while, famous conjectures, and they're very, very tricky, very tricky. This was proved 10 years later, and this was proved 17 years later. That paper was 1933. And as I say, I defy anybody who thinks come up with the blackboard without operation. Kindergarten maybe a little. with Iraqi and Sakai, it's only members of it. But anyway, Halle did do a lot about the theory of states, so I don't have to say too much about that. I mean, I can assume that maybe it's an unfair assumption. Maybe I'll just wing some things through here. Yeah. Excuse me. So the problem that we run into is the following. The problem with what Dirac is doing is he needs delta functions. We need a mathematical theory of states to replace that, whatever that is. If you were at Alice talk, remember it, fine. If not, I'll give you a brief, very brief picture. Here's some of the notation I was talking about, and I'll tell you things that are going to be interesting and fun to you anyway. If you're asking yourself what a general orthonormal basis is, you really conclude pretty rapidly that you simply have to identify it with the orthonormal basis has to be identified with the maximal abelian self-adjoint the masses in the Hilbert space. Each one is a generalized orthonormal basis. And in fact, you can do what are now mathematical miracles. You can take the diagonal parts of things relative to these bases. It's a diagonalization process. The matrix that ought to be there, you can take its diagonal part relative to these bases. In the case of completely continuous bases, we'll get around to that in a moment, it turns out that the diagonal part, really what the question that Dirac is proposing, didn't propose it, the question is simply asserted. Try to do it very carefully mathematically, it turns into a question. Has, as a sub-question, is this diagonal part relative to an orthonormal basis? Is it unique? Are there many different diagonal parts? That's a very strong form of asserting non-uniqueness. And what Singer and I did in this paper in 1959 journal was to show that for the continuous, totally continuous orthonormal bases, I'll describe that to you in a moment. The diagonal part need not be unique. And it's done with Fourier analysis, completely with Fourier analysis. It's rather tricky. And it's done by playing off, it's done really by physical inspiration. It's done by playing off the position massa, position space, against the momentum massa. You don't see that happening. When you look at the paper, you won't see that happening in there. You'll see, but that's what's happening. What we did was to reach in to that way of doing things without using it in an abstract structural way, and just pull out the analytics that we needed, the pieces that we needed to do this. But it's a construction of a counterexample, so to speak, and it gives us the result that I just mentioned. So what Dirac is asserting at the end is in mathematical form wrong. The basis is not unique in the case of continuous. You can extend that the basis itself is not unique. The continuous basis, you can choose it in different ways. I suspect there's physics in that, and the data may actually be in the literature. It's something that and I think some other people have begun to think that there's more uncertainty than one sees in the physics. Something, I have a folder that called essential uncertainty. But I haven't had time over the years. I haven't had time to drop everything. I'd have to retool it to do that. But I think the fact that Dirac is wrong there says that there's some phenomenon going on in quantum mechanics. It hasn't been mined as yet. Well, who knows? We'll see that later. Let's see why injection. But let me talk to you a little bit more about these general orthonormal bases. What are they? Well, let me give you an example. Start with I don't want to get too technical. It's a sigma finite measure space. S mu, S space mu is measure, I know we'll talk about measure algebra, measurable space. And look at L2, our Hilbert space is L2 of this measure space. It can also be countably separated because we're really only interested in the separable Hilbert space. And take an essentially bounded measurable function f and associate with that an operator on L2 as follows. The multiplication operator, multiplication by f. Mf of g is f times g. And the collection, gather together the collection of all those multiplication operators, that is a maximal abelian self-adjoint algebra. Now, let's get a little more specific. Suppose S is the unit interval 0 to 1. Doesn't matter. And your measure is Lebesgue measure on it. Then that multiplication algebra equals A sub C, C for continuous. And I told you about the finite, those are finite matrices, diagonal matrices, or infinite diagonal, bounded infinite diagonal matrices, A sub D. And then the space that has one part that's continuous and the other part, n atoms, n points, each with positive measure, that would be, algebraically, would be topologically, would be direct sum of AC and AN, or AC and AD. And here is theorem. Right down at the bottom. Let's see. Yes. Here's grade theorem. Each massa, each self-adjoint maximal abelian algebra on a separable Hilbert space is unitarily equivalent to one of these four types. That's all there is. You'd never believe that something can be that, at this level, can be that simple. Narrowed down to that. And it's essentially, this is essentially a result of a Neumann. He didn't say it this way, these terms, but he proved that any abelian algebra of this nature, strong, closed in the strong operator, certainly the maximal abelians. Well, let me just say, he proved that any maximal abelian algebra is generated on a separable space, is generated by a single self-adjoint operator. Take all functions, all polynomials in it, and close it up relative to convergence on vectors. It's a beautiful construction. You want to go to bed happy, just spend an hour studying that. And from that, you get this, So I was saying before, one of the approaches to asking yourself, what are these vectors? What are the delta functions of Neumann, of Dirac? One approach is, as I say, the points of 0, 1, race, and their delta functions. The other approach is the expectation function. corresponding to the unit vector of is certain functions on the maximal abelian algebra. I'll describe that now. So the states, well, one example of a state would be given to you by the unit vector x in the Hilbert space and the associated expectational functional on bounded operators, a of h, omega x, ax in front of x. Out of homage to Dirac, I use the angle brackets, but I don't go the whole way of using these broad vector terms. Mine are linear in the first, but most mathematicians, linear in the first variable, conjugate in the second. Dirac physicists tend to normalized, of course, omega x, the identity, that means you're using a unit vector. And with the crucial property that the self-adjoint operator with spectrum is real and non-negative, will have expectation greater than or equal to 0. And those are called vector states. But there are other states, many other states of B of H. The state, as Paolo was describing it this morning, is a functional on B of H, positive on positive operators, and 1 at the identity operator. Those states that restrict to our generalized orthonormal basis, maximal abelian algebra, and turn out to be multiplicative on the algebra. So a homomorphism into the complex numbers. Those are the vectors, the diagonalizing vectors, those functions themselves, states that diagonalize. This also has to do with pure states. Paolo spoke about pure states this morning. I don't think he mentioned that the GNS representation is irreducible, if and only. Did you mention that, Paolo?
But it went so fast.
It went fast. Yeah, you went fast for my GNS representation is irreducible if and only if the state is pure. And now I tell you that each of these vector states corresponding to a unit vector is a pure state of B of H. Which is to say, so the set of, I guess you did this too, didn't you? The set of states forms a convex family. I heard that was you. The pure states are the extreme points, states that are not expressible as a convex combination of two distinct states, a proper convex combination of two distinct states. So the extreme points for a convex set, if you don't know these things, are points like the vertices of a triangle. By now, he knows everything. So the vector states are pure states of B of H. But they're not the only pure states of B of H. As a matter of fact, there are 2 to the C power of the continuum. Other pure states. Lots of them. And every one of them annihilates the compact operators. Unlike these vector states, which would be 1 at the one-dimensional projection generated by the vector. That's fun. So those other states, one tends to, ones that annihilate the compact operators, one tends to call singular states. So Dirac's question becomes the following. Dirac's question becomes this. If you have a massa, and if you have a multiplicative nonlinear homomorphism, multiplicative nonlinear function, multiplicative non-zero function, linear function, sorry. Then it must be more integrated. So it has a unique pure state extension, and it will follow from that. There's a little argument. It will follow from that it has a unique state extension. It has a unique pure state extension to B of H. That's what Dirac is asserting. He says that it's completely determined up to phase. He's talking about the basis. And he's wrong about that. He's right in the case of AD. Let's stick with infinite dimensional subgroups. He's right in the case of AD if you're talking about the vector states. But there are singular, many, again, 2 to the C, singular states of AD, the algebra of diagonal matrices, the things that don't correspond to the diagonalized basis. That algebra is actually the same as the algebra of continuous functions on the Stone-Check compactification of the integers, the beta compactification of the integers. And all the points other than the integer points give you pure states of that AD. And now the question of whether those pure states are uniquely extendable was one that is an I left open back in 1959. We proved some things, lots of things about them. We had done, in some sense, I would point out, we had done our job. The problem at the time was just Dirac and any basis. And we had shown that when there's a continuous part, there are none that are states without a unique extension. But there is an I inclined to the view, that's the way we put it, we inclined to the view that pure state extension was not unique for the other states, the states other than the integer states. And that's the problem I'm talking about. Now, we had some sort of technique for doing all these things. We used something that Bernard had done back in 1943, part of his diagonalization process. He invented that. By the way, the diagonalization process is something that's come to be of great importance. It's a non-commutative conditional expectation. And we showed that such things, even those things, were not unique. We use that technique, that diagonalization technique, to set things up, to bring things to a point where if you could contradict something, and that's where the Fourier analysis came in. Using that to construct our counterexample. They said even that was inspired by the physics, the uncertainty of measuring canonical coordinate momentum with complete accuracy. We left open that question. I lost the third. We left open that question of whether that pure state extension, but we proved a lot of other things. We proved that pure state extension was unique to large classes of operators. So all kinds of issues and problems sprang out of that. And that diagonalization technique was extended, reformulated in a very clever way by Joel Anderson, who's done a lot of very nice work on this, notably in a paper in the 1979 Transactions in Mathematics, Transactions of the American Mathematical Society. And Joel reformulated the question to a finite matrix question. Which has come to be known as the paving question. This is the same as the uniqueness question, but now instead of it being highfalutin and phrased in language of operator algebras, directly part of the formulation of quantum mechanics, it comes down to some very simple, unbelievably simple looking question. Given a positive epsilon, here it is as an assertion. Is this true? That's the question. Is this true? Given a positive epsilon, there's a positive integer r, such that for every finite matrix of whatever order n, that's very important, the epsilon is given, the r must be found before you know the n. So it has to be there for all n, such that if you now choose the n and a matrix T of order n with 0 diagonal, the numbers 1 through n can be partitioned. That's where paving comes in. Paving partition can be partitioned into r or fewer sets. So the AJs are mutually exclusive, disjoint, mutually disjoint, with union the numbers 1 through n, such that for each j, each one of these sets, qjt, qj in norm is less than or equal to epsilon times the norm of t. And what's qj? I didn't write it down, but it's the projection, diagonal projection, that has a 1 at every diagonal entry corresponding to a number in the set aj. So it's a little, I mean, for a totally elementary and trivial statement, you can tell this to your linear algebra students. They probably won't do it. So, how are we doing? We're at 5. Okay. I'm supposed to stop at this point? I stop at this point. Okay. So this is the, pardon me? Yeah. No, I'm cool. You want to ask questions? No. Yes?
Yeah, you mentioned 17 years after Galva and Naimark had the original thing, and some guy extended their work to a simplifying x, and who was the person?
I'm going to blush. Jim Glim and I, for that question. The isometry. The other one was pretty much Kaplansky and a Japanese mathematician who was running the great functional analysis group at Sendai, Fukiamiya. So-called symmetry.
Okay, maybe one. When I learn quantum mechanics, they tell me that when you have an operator, it's a measure, and then the thing will collapse to a pure state, and then you measure.
When you measure, what you're saying, I think, if I may, you have an observable, and when you make a measurement, it jumps into an eigenstate.
Yes. How does your result confuse my physics? Or does physics confuse me? Or what's going on with that picture?
It may be, yes, I see, this is the essential uncertainty I'm talking about. You see, you can't really prepare these pure states so that you jump into, you have an exact eigenstate. I mean, you can approximate to them as closely as you can set up the apparatus so that you can approximate to the pure state as closely as you want. And what the other thing is saying, what we're saying is you may be able to set the apparatus up and approximate to this same state, but so that you may be able to approximate, you may be able to approximate to another pure state of the whole system that will give you the same measurement and the same pure state for this particular observable and its functions, which is the massa you're thinking about.
Do you mean that
you're not really set, well, briefly put, you don't set up the kind of pure state we're talking about for this kind of measurement in your physical system. You can't do it. Can you get me a pure state that will measure a particle that's moving back, oscillating back and forth on the real line, so that it measures this particle exactly at the position pi over 7? Exactly at that transcendental number. But you can approximate as closely as you want to that. You can set the apparatus, you can set the state. You can put the screens around, and so on and so forth, so that you get that as closely as you want. But you can't set it up exactly. And what's being said is you can make the same approximation to that pure state of the position observable algebra with some apparatus that is actually setting up another state. And I think you can probably measure that. I think that data is probably in the literature, so you know how to pull it out.
So do you mean that your two orthogonal bases means you can have two different sequences can converge to one?
Not to one vector, but to one state. Yes, that's exactly what happened. But be careful. This is so damn delicate. You can't do it with sequences. You've got to do it with nets. Just like you can't converge the points of the beta compactification off the integers with integers. Sequences. You're up in wild territory. But and Mackie and I were very close friends. Really liked one another very much. We had a furious argument one time about this public argument. Arthur Whiteman's 60th birthday party. That's a beautiful story. Really, public argument. I just split the whole community. I have to say, sadly, so I can was with Mackey. Mackey lost that argument in purely mathematical terms. But Wigner was with Mackey, and John Archibald Wheeler was with me. Anyway, but it's just this kind of, see, Mackey claimed, he said, look, all that stuff off the diagonal, this problem. Mackey said, he said, that's all. And here's what happens. Mackey was sort of sleeping a little bit. We've always talked about it. We come together every time we hear one another. Talk this sort of stuff, philosophical stuff. And Mackey, and he popped up and he said, yeah, no, he was saying, well, he said, it's the orthonormal basis that's really important. And the other states, he says, that's all. And he was like mumbling all this under his breath. And then at a certain point, he said, garbage. And so the only word that came through was the garbage. I felt I had to defend it, and spiraled out of orbit. With Barry Simon sitting there acting as interpreter. Barry's a smart guy, knows a lot of stuff. He was acting as an interpreter for this business, mathematical stuff, to very largely physics audience that was sitting there. And at a certain point, Mackey said something or other, and I said, but what about the Rees-Mogg law? Barry said, yes, what about the Rees-Mogg law? Mackey was sort of flattened there. But what Mackey was doing was saying, Mackey was moving toward constructivism. Do you know what that is?
I suggest maybe
We better do it.
Yeah.